And now in this lecture we find out the radius of the small circle. In the drawing we have a quarter circle. AOB is a quarter circle. Inside this quarter circle we have a semicircle. This is a semicircle. And also this circle, this small circle. And our mission to find out the radius of this semicircle or the value of capital R. That is the radius of this small circle. In addition, we know actually that OB equals to 16 units in its length. OB is actually the radius of the quarter circle, so we know that the radius of the quarter circle equals to 16 units, and therefore AO is also the radius of the quarter circle that is also equal to 16 units in its length. And the radius of the quarter circle AO is also the diameter of this semicircle. So we know that the diameter of this semicircle AO equals to 16, therefore the radius must be 16 over 2, that is 8. So the radius of this semicircle equals to 8 units in its length. We define the center of this semicircle, this point is point P. So the radius or AP of this semicircle equals to 8 units in its length. And the radius PO of this semicircle, it is also equals to 8 units in its length. AOB is a quarter circle, therefore angle AOB must be equal to 90 degrees in its size. This angle must be equal to 90 degrees in its size. Here we can implement rule 1 in this small circle. Repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have this circle and we have tangent AB that is tangent to this circle here at point M. Point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We can actually implement rule 1 in our drawing. Because in our drawing, before that we define the center of this small circle, this point as Q. And we define the point of tendency of tangent OB with this small circle, this point as point M. So we have here the radius QM of this small circle that is equal to R is drawn to point M, that is the point of tendency of tangent OB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from point Q, we will draw perpendicular on AO. Again, from point Q, we will draw perpendicular on AO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we actually created a quadrilateral AQMO. Inside this quadrilateral, we created quadrilateral HQMO. Inside this quadrilateral HQMO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrilateral HQMO, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at this rectangle, if not a square. So we can relate to this quadrilateral HQMO as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle HQMO, side QM must be equal to the opposite side edge O. But QM equals to R, it is the radius of the small circle, that is equal to R. Therefore edge O must be also equal to R. So what is the length of this line segment PH? Although it is very easy to see that PH equals to PO minus edge O. And again, PH equals to PO minus edge O. So I write it down. PH equals to PO minus edge O. So PH equals to PO. PO is 8, it is the radius of the semicircle, that is equals to 8 units in its length, minus edge O. We just write down order that edge O equals to R. So in total, PH equals to 8 minus R. PH equals to 8 minus R. Although here we define the touching point of this small circle with this semicircle, this point is point S. Again, point S is the touching point of this small circle with this semicircle. And here we can implement rule 10. I'll build quickly on rule 10. According to rule 10, if two circles touch each other externally, here in the drawing we have this small circle touches this big circle at this point, point P. Point P is the point of tendency of the touching point of this small circle with this big circle. And we know that the center of this big circle is located here at point O. The center of this small circle is located here at point M. According to this rule 10, the straight line that connects their centers together, that is to say, the straight line MO must pass through their touching point, that is actually point P. So the straight line MO must pass through point P, or MPO is one straight line. Again, MPO, according to rule 10, is one straight line. So whenever you have two circles that have an external line between them, like here, that is to say they are touching each other externally, then the straight line that connects their centers together, in this case it is the straight line MO, must pass through their touching point, that is actually point P, or MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing, this small circle touches this semicircle and this point S. Point S is the touching point of the point of tendency of this small circle with this big semicircle. The center of this small circle is here at point Q. The center of this semicircle is here at point P. So according to rule 10, the straight line that connects the centers together is of course the straight line QP. So the straight line QP must pass through point S. So the straight line QP must pass from point S. Or QSP is one straight line. Again, QSP is one straight line. Okay. So the straight line QP must pass through point S, according to rule 10. Okay. You can see here that the straight line QP, that is the straight line that connects the centers together, passes through point S, that is the attaching point. QSP is one straight line, or QP is also one straight line. What is the definition of line segment PS? Line segment PS starts from point P, that is the center of this semicircle, and ends at point S, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, that is equals to 8 units in its length. So PS equals to 8. What is the definition of line segment SQ? Line segment SQ starts from point Q, that is the center of this small circle, and ends at point S, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QS is the radius of this small circle, that is equal to R, or capital R. So in total, the length of line segment PQ is 8 plus R. So I write it down. PQ equals to 8 plus R. And the reason that PQ equals to 8 plus R is because of the fact that PQ is one straight line. Okay? Actually, PQ can be equal to 8 plus R only and only if PQ is one straight line. Otherwise, if PQ is one straight line, is not one straight line, then the length of PQ will be definitely greater than 8 plus R. Again, the only reason that PQ equals to 8 plus R is because of the fact that PQ is one straight line. And we prove that it's one straight line because the straight line that connects the centers together passes from point S. Okay. Now I'll copy the right triangle PHQ. I'll copy the right green triangle PHQ in a new page, and we'll implement the Pythagoras theorem in this right green triangle PHQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. PH equals to 8 minus R units in its length. The hypotenuse, we just said now, hold on, that the hypotenuse PQ equals to 8 plus R. Inside HQ is the missing side, so we leave it as it is. So here, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right green triangle PHQ that I got from the original drawing. In this right angle PHQ, according to the Pythagoras theorem, the square of the hypotenuse, that is PQ square, must be equal to PH square plus HQ square. So I write it down, according to the Pythagoras theorem, in this right angle triangle PHQ, PQ square equals to PH square plus HQ square. PQ equals to 8 plus R, therefore PQ square is 8 plus R square, and it is equals to PH square. PH is 8 minus R, therefore PH square is 8 minus R square plus HQ square. HQ is the missing side, so we leave it as it is. So actually, according to equation 1, we actually found out that 8 plus R square equals to 8 minus R square plus HQ square. Here we will open the brackets on both sides of this equation, equation 1, and we get that according to this equation, equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square plus 2 times 8, that is 16 times R. So it is plus 16R, and it is equals to 8 minus R square. 8 minus R square equals to 8 squared, that is 64, plus R square minus 2 times 8 is minus 16 times R, so it is minus 16R plus HQ square. So here we have 64 on both sides of this equation, equation 1. So 64 we get cancelled. And we have also R square on both sides of this equation, equation 1, so R square will also get cancelled. After cancelling those two expressions, we left in this side of the equation 1, we left only with 16R. So 16R equals to, on the other side of this equation 1, we have minus 16R plus HQ square. So here we get 16 out to this equation, equation 1, and we get that according to this equation, equation 1, 16R plus 16R is 32R, so in this side of this equation 1 we have 32R, and the other side of equation 1 we have only with HQ square. So according to equation 1, 32R equals to HQ square. We know that 32 is 16 times 2, so we substitute 32 by 16 times 2, so it is 16 times 2R, this equals to HQ square. So here we take a root out of this equation, equation 1, we find get that according to this equation, equation 1, HQ equals to the square root of 16 times 2R. The square root of 16 is 4, so inside the root we left only with 2R. And we actually found out that the length of line segment HQ equals to 4 times square root of 2R. Yes, so actually this side HQ equals to 4 times square root of 2R. But we already found out that HQMO is rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle HQMO, side HQ must be equal to the opposite side OM, but HQ is 4 times square root of 2R, therefore OM is also 4 times square root of 2R. Actually, the small circle have an internal notch with this big quarter circle at this point. That is to say, they are touching each other internally at this point. We define that the touching point here. This point is point C. So here we can implement rule 9. Repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, here, this small circle touches this big circle here at this point, point P. Point P is their point of tendency or their touching point. So whenever you have two circles that touch each other internally, then the straight line that connects their centers together, the center of this big circle is at point O, the center of this small circle is at point M, and the straight line that connects their centers together is the straight line OM. So the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass for point P. OMP is one straight line. Again, OMP is one straight line. You can actually implement all 9 in our drawing. Well, as I mentioned before, this small circle touches the big quarter circle here at this point, point T. Point T is the touching point. The center of this big quarter circle is here at point O. The center of this small circle is here at point Q. And the straight line that connects their centers together is of course the straight line OQ, and according to rule 9, the straight line OQ must pass through point T, that is their touching point. OQT is one straight line. Again, OQT is one straight line. Repeat again, this straight line, this is one straight line, OQT. What is, if OQT is one straight line, it means that OT is also one straight line. But what is the definition of straight line OT? The straight line OT starts from point O, that is the center of this quarter circle, and ends at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle, that is equals to 16 units in itself. So right now, we should find out that OT is the radius of the quarter circle, that is equals to 16 units in its length. What is the definition of this line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and then at point T, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, QT is the radius of this small circle, that is equal to R. So QT equals to R. What is the length of this? What is the length of this line segment QO or OQ? OQ, for the moment, it is very easy to see that OQ in total equals to OT minus QT. Again, OT minus QT equals to OQ. So I write it down. OQ equals to OT minus QT. So OQ equals to OT, that is 16, minus QT, that is R. So in total, OQ equals to 16 minus R. I write it down. OQ equals to 16 minus R units in its length. In the next step, I will copy the right blue triangle OQM. This right blue triangle OQM in a new page, and we will implement the Pythagoras theorem on this right blue triangle, triangle OQM. The hypotenuse OQ equals to 16 minus r units in its length. Side OM equals to 4 times square root of 2r. And finally, QM is the radius that we are looking for in this question, is the radius of this small circle that is equals to r. So here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle, the right blue triangle, triangle OQM with the coordinate from the original drawing. In this right triangle OQM, according to the Pythagoras theorem, OQ square equals to OM square plus QM square. Again, OQ square equals to OM square plus QM square. So I write it down. OQ square, that is the square of the hypotenuse, equals to OM square plus QM square. OQ is 16 minus r, therefore OQ square is 16 minus r square, and it is equal to OM square. OM is 4 times square root of 2r, and therefore OM square is 4 times square root of 2r square, plus QM square. QM is r, therefore QM square is r square. So according to equation 2, we shall find out that 16 minus r square equals to 4 times square root of 2r square plus r square. Here we open the brackets on both sides of this equation, equation 2, and get that according to this equation, equation 2, 16 minus r square equals to 16 squared, that is 256 plus r square, minus 2 times 16 is minus 32 times r, so it is minus 32r. It is equals to, in the other side of this equation, equation 2, we have 4 times square root of 2r square is equals to 4 squared, that is 16. And here the power, we cancel the root and we left only with 2r. So 16 times 2r plus r square equals to 256 plus r square. So here we have r square on both sides of this equation, equation 2, so r square will get cancelled. After r square gets cancelled, in this side of equation 2 we left only with 256 minus 32r, that's equal to 16 times 2r is 32r. So according to equation 2, I shall find out that 256 minus 32r equals to 32r. Here we let 32r to this equation, equation 2, and get that according to this equation, equation 2, (256) equals to 32r plus 32r is 64r. So according to equation 2, 256 equals to 64r. We will divide this equation, equation 2 by 64, and get that according to this equation, equation 2, r This is the radius that we are looking for in this question. That is the radius of the small circle. R equals to 256 over 64 is 4. So R equals to 4 units in its length. Repeat again. The radius of this small circle R equals to 4 units in its length. So in the next step I will summarize the lecture. In this lecture we found out the radius of this small circle, or we found out the value of R. That is the radius of this small circle. In the drawing we have a quarter circle, AOB is a quarter circle. Inside this quarter circle we have this semicircle, this is a semicircle, and we also have this small circle. Again, our mission is to find out the radius of this small circle that is equal to R. We have to find out the value of R. So, first of all, we define the center of this semicircle at this point as point P. We define the center of this small circle at this point as point Q. And we know actually that the radius of the quarter circle equals to 16, according to what is given in the question. So AO equals to 16, and OB is also the radius of the quarter circle that equals to 16 units in its length. But the radius of the quarter circle is also the diameter of this semicircle. Again, the radius of this quarter circle is also the diameter of this semicircle. So we know that the diameter of this semicircle AO equals to 16. If the diameter is 16, it means that the radius must be equal to half of it, that is 16 over 2, that is 8. So the radius AP of this semicircle is 8, and the radius PO of the semicircle is also 8. Okay, and we also know that AOB is a quarter circle, therefore this angle equals to 90 degrees. Here you can implement rule 1. According to rule 1, because of the fact that we have the radius QM that is drawn to point M, that is the point of tendency of tangent OB with this small circle, and whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MQ. If OB is perpendicular to MQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. The next step we did the construction, that is to say from point Q we do perpendicular on AO. Again from point Q we do perpendicular on AO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and AO. This point is point H. By doing this construction, we created here quadrilateral edge OMQ. Inside this quadrilateral edge OMQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 450 angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 450 angle must be equal to 90 degrees in its size. So inside this one quadrilateral edge QMO we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be its rectangle, if not a square. So we relate to this quadrilateral edge QMO as rectangle because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle edge QMO, side QM must be equal to the opposite side edge O. But QM is R, therefore edge O must be also equal to R. Okay, and here we have we can implement rule 10. Why? We have this small circle that touches this semicircle at this point. Point S is the touching point. It is the touching point of this small circle with this semicircle. They touch each other at point S. So according to Therefore, we can implement here all 10. According to all 10, whenever you have an external notch between two circles, that is to say they are touching each other externally, then the following rule is true, that if two circles touch each other externally, like here, this small circle touches this big circle at this point, point P. So, according to this rule, all 10, the straight line that connects their centers together, the straight line, the center of this small circle is 0.m. The center of this big circle is 0.0. And the straight line that connects the centers together is of course the straight line MO. The straight line MO must pass through their touching point at this point P. Again, the straight line MO must pass through their touching point at this point P. Or MPO is one straight line. Again, MPO is one straight line. We can implement all 10 in our drawing. In our drawing, we have, again, this semicircle touch this circle at point S. Point S is the touching point. So, in the center of this small circle is at point Q. The center of this semicircle is at point P. And the straight line that connects the centers together is the straight line PQ. So the straight line PQ must pass through point S, that is their touching point. Or PSQ is one straight line. Again, PSQ is one straight line, according to rule 10. And of course, PQ is of course a straight line. So, what is the definition of PS? Line 7 PS starts from point P, that is the center of this semicircle, and ends at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, PS is the radius of this semicircle, is equal to 8 units in its length, according to what we have already found out. What is the definition of line 7 QS? Line 7 QS starts from point Q, that is the center of this small circle, and ends at point S, that is the point on the circle or the small circle itself. So this is exactly the definition of radius. Therefore, QS is the radius of this small circle is equal to R. So in total, PQ equals to PS plus SQ. So PQ in total equals to PS, that is 8, plus QS, that is R. So in total, PQ equals to 8 plus R. Yeah, PQ equals to 8 plus R. And what we already found out that the length of this line 7 PH equals to PO minus HO. So PH equals to PO, that is PH equals to PO, that is 8 minus HO, that is R. So PH in total equals to 8 minus R, and the hypotenuse of the great triangle PQH equals to 8 plus R, and HQ is the missing side. So I copied the right great triangle in a new page and implemented the Pythagoras theorem from this great right triangle PQH. This is the right triangle PQH that I copied from the original drawing. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle PQH, it means that PQ square equals to PH square plus HQ square. Again, PQ square equals to PH square plus HQ square. So PQ square, PQ is 8 plus R, therefore PQ square is 8 plus R square, and it is equals to PH square. PH is 8 minus R, therefore PH square is 8 minus R square, plus HQ square. HQ is the missing side, so we leave it as it is. So in total, actually, according to equation 1, we found out that H plus R square equals to 8 minus R square plus HQ square. Here we open the brackets on both sides of this equation, equation 1, we finally found out that according to this equation, equation 1, 8 plus R square equals to 8 squared, that is 64, plus R square, plus 2 times 8, that is 16, times R. So plus 16R, and it is equal to 8 minus R square. 8 minus R square equals to 8 square, that is 64, plus R square, plus 2 times 8 is minus 16, times R. So it's minus 16R, plus HQ square. Here we have 64 on both sides of this equation 1, so 64 will get cancelled. And we have R square also on both sides of this equation 1, so R square also will get cancelled. So what is left from this equation 1 after we cancel those two expressions? What is left that in this side of equation 1 we left only with 16r. On the other side of equation 1 we left only with 116r plus hq squared. Here we added 16r to this equation, equation 1, and found out that according to this equation, equation 1, 16r plus 16r is 32r. So 32r equals to hq squared. 32 is 16 times 2, therefore substitute 32 by 16 times 2. And finally found out that according to equation 1, 16 times 2r equals to hq squared. Here we took a root out of this equation, equation 1, and finally found out that hq equals to the square root of 16 times r. The square root of 16 is 4, so inside the root we left only with 2r. So in conclusion, we found out that hq equals to 4 times the square root of 2r. So here HQ, this is line segment HQ, this equals to 4 times square root of 2r. But we already found out that quadrilateral HQMO is a rectangle. We also know that the opposite sides of rectangle are equal to each other. So in rectangle HQMO, side HQ equals to the opposite side OM. But HQ equals to 4 times square root of 2r, therefore OM must be also equal to 4 times square root of 2r. And here we implemented also rule 9. Why? Because we have here this small circle touches the big quarter circle. Here this point T is the touching point of this small circle with this big quarter circle. And for that reason, we have here an internal notch between the small circle and the big quarter circle. And for that reason, we can implement here rule 9. What is rule 9? According to rule 9, if two circles touch each other internally, here, this small circle touches the big circle at point P. Point P is their point of tendency. Then the straight line that connects their centers together, the center of the big circle is at point O. The center of this small circle is at point M. And the straight line that connects their centers together is the straight line OM. So the straight line OM must pass through their touching point. Or the straight line OM must pass through point P, that is their touching point. Or O and P is one straight line. Again, O and P is one straight line. We can definitely implement rule 9 in our drawing. Because in our drawing we have, as I already mentioned before, the small circle touches the big quarter circle at this point, point T. Point T is the point of tendency of their touching point. And therefore, we know that the center of this small circle is at point Q. The center of this big quarter circle is at point O. And the straight line that connects their centers together is the straight line OQ. According to rule 9, the straight line OQ must pass from point P, that is their touching point. Again, the straight line OQ, that is the straight line that connects their centers together, must pass from their touching point, that is point T. Or OQT is one straight line. Again, OQT is one straight line. But if OQT is one straight line, it means that OT is one straight line. So what is the definition of line segment OT? Line segment OT starts from point O, that is the center of the quarter circle, and ends at point T, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OT is the radius of this quarter circle. That is equal to 16 units according to what is given as the question. So OT equals to 16. What is the definition of line segment QT? Line segment QT starts from point Q, that is the center of this small circle, and ends at point T, that is the point of the small circle itself. So therefore QT is the radius of this small circle, is equal to R. So QT equals to R and OT equals to 16. So what is the length of QO? QO equals to QT. What is the length of QO? QO equals to OT plus QT. Again, OT plus TQ equals to QO. Repeat again, QO equals to OT plus QT. So QO, this line segment QO, this is actually the hypotenuse of the blue triangle. Therefore, QO equals to TO, that is 16, plus QT, that is R. So in total, the hypotenuse QO equals to 16 minus R. So in the next step, I copy the right blue triangle, QOM in a new page and implemented the Pythagoras theorem on this right triangle, triangle QOM. Actually, this is the right triangle, triangle QOM. I copy it from the original drawing. We just right now found out that the hypotenuse QO equals to 16 1 R units in itself. QM is the radius that you're looking for. In this question, it is the radius of the small circle that is equal to R, and OM equals to 4 times square root of 2R. So according to the Pythagoras theorem, in this right triangle QOM, QO square equals to QM square plus MO square. Again, QO square or Q square equals to OM square plus MQ square. QO is 16 times R, therefore QO square is 16 times R square, and this equals to OM square. OM equals to R, therefore OM square equals to R square, plus QM. QM equals to 4 times square root of 2R, therefore QM square equals to 4 times square root of 2R square. So according to equation 2, we found out that 16 plus R square equals to 4 times square root of 2R square plus R square. We open the brackets of this, both sides of this equation 2. We found out that according to equation 2, 16 plus R square equals to 16 squared, that is 256, plus R square, minus 2 times 16 times R, this is minus 32R. And this equals to 4 times square root of 2R square. 4 times square root of 2R square equals to 4 squared, that is 16. And here the root cancels the power and we left only with 2R. So according to equation MQ is R, therefore MQ square is R square. So according to equation 2, we actually found out that 256 plus R square plus 32R equals to 16 times 2R plus R square. So here we have R square on both sides of this equation 2, so R square will cancel. After we cancel R square, in this side of equation 2 we left only with 256 plus 32R. In the other side of this equation 2 we left only with 32R, because 16 times 2R is 32R. So according to equation 2, we should find out that 256 plus 32R equals to 32R. Here we added 32R to this equation 2, and finally found out that 256 equals to 32R plus 32R is 64R. So according to equation 2, 256 equals to 64R. Here we divide this equation 2 by 64. And finally found out that according to this equation 2, R equals to 256 over 64, that is 4. So we found out that the radius of this small circle R equals to 4 units in its length. Okay, thank you very much.